math stuff yet, and there was no point. Okay, we could have done some math on Boyle's law, we could have done some on Charles' law, we could have done some on Gay-Lussac's law. We could have done all that individually, or we could just do it all together, and that's what we're going to do right now. And this is called the combined gas law. This takes care of all those things for you. So it does Boyle's law, it does Charles' law, it does Gay-Lussac's law, and it does what we call the combined gas law, which is what happens if all, before with Boyle's law, it only does pressure and volume. Charles' law does volume, temperature. What happens if the pressure and the volume and the temperature are changing? Well, those laws aren't going to work for us. So we need to do combined gas law. By the way, combined gas law looks like this here. So you're going to write this down. Like so. Okay? P1 V1 over T1, initial conditions. P2 V2 T2 over T2, I should say, final conditions. Okay? 6 variables up here. 6. Okay? And we need to be able to solve for one of those. Okay? In some cases. Now, like I said, combined gas law can be used for any closed system going through a change in pressure, temperature, and volume. As usual, temperature must be in Kelvin, as always. Okay? So when you look at T1 and T2 there, you better have it in Kelvin. Otherwise, it's going to be obviously very, very wrong. All right? So here we go. Ready for some examples? By the way, if you're saying, well, geez, I kind of really miss doing Boyle's law. Really wish I had that formula again. Guess what? Well, Boyle's law says the temperature has to be the same. Look. If the temperature is the same, can I just do that? If they're both the same, the temperature, if they're both constant, can I just do that? The answer is yes, in case you're wondering. That's Boyle's law. P1 V1 equals P2 V2. You might say, well, what if I wanted to do Charles' law? Well, look. If the pressure remains the same, that's part of Charles' law. Charles says V1 over T1 equals V2 over T2. That's Charles' law. That's part of this formula. Okay? And of course, we can do all three if we wanted to, combined gas law, or we could do Gay-Lussac's law. We cover up the volumes, P1 over T1, P2 over T2. All those formulas are there for you. That's why I don't show you individually. It doesn't make sense. It's kind of almost a waste of time if you ask me. Okay? This formula does everything. And in fact, in some cases, we won't use all these variables, and I'll show you some examples with that today. So here we go. Let's look at the first one here. I'm going to have to do this on a different page, and sorry, I didn't leave you a lot of room there. I apologize for that. But I'm going to go to a different page here, and then I'll just read it off here. It says a 15-liter weather balloon is released under STP conditions. After 10 minutes, the balloon has a temperature of minus 38 and a pressure of 80.5. Calculate the new volume of the balloon. Okay? So you have to read through all that and decide, okay, well, here, you know what? Start with this, because guess what? All questions will start with this for now. What letter am I looking for here? What variable in this big scheme of things here, all 6 of these, which variable am I looking for? It says calculate the new volume of the balloon. Which one am I looking for? What do you think? Yep. V2. How are you going to solve for V2 is the question. Once again, that's kind of up to you. If you don't know, I guess you should watch me. If you want to do this on your own, go ahead. I don't care, but you need to be able to solve for V2. I would, of course, my favorite 2 words, cross multiply. So I do this, P1 V1 T2, and then equals that, T1 P2 V2. Okay? I cross multiply. And of course, V2 is not by itself yet, so I would say, oh, how am I going to get V2 by itself? I would say, well, I probably should divide by T1 P2, so I can cancel that out and cancel that out, and then I divide by T1 and P2 here. Right? What I do to one side, I do to the other side. Right? T1 P2, T1 P2. Yes? If you got a different system, that's fine. I don't care. Make sure, at the end, I'm going to give you a little more time on the next one here. You come up with P1 V1 T2 over T1 P2 is the formula. You don't have to have them in exact order. If you had T2 out in front, that's fine. If you have P2 and T1 at the bottom here flipped around, I don't care. It doesn't matter. You just multiply them. It doesn't matter. Okay? But that's what you're looking at for the formula. That's what you need to be able to come up with. Okay? If you need help with that, if you need practice with that, I got some other ways of doing that for you. I can do that for you. That's what I do. It seems to work. Okay. All right? But it's up to you. Like I said, let me know. Okay. So we go to the question now. What do we have here? Well, I like to put in some brackets here because I know I got 3 things across the top and I got 2 down here. Okay? Well, once again, we got to kind of go through the question here. So it says, a 15-liter weather balloon is released under STP conditions. Those are all my initial conditions. 15-liter, that would be V1. That's going to go here. V1, initial volume. Under STP conditions. What does STP mean? Stone Temple Pilots? No, that band broke up, right? They became Velvet Revolver. You guys don't know what I'm talking about, that's fine. Anyway, what is STP? STP was a band back. Never mind. Okay. STP means standard temperature and pressure, right? That was one of the things we looked at yesterday. Back at the periodic table, get them out, let's go. STP, look it up. Come on. STP, standard temperature and pressure. That'll tell you that, in fact, right here, it's at the top there, of course, STP. 101.325 is standard pressure. Standard temperature is 273.15. That, of course, is T1. P1, V1, T1 are the ones that I have so far. Okay? Then the question goes on to say, has a temperature now after 10 minutes. 10 minutes goes where in this question? 10 minutes goes nowhere, yes? I don't care about the time. There's no time variable up here. It's pressure, volume, and temperature. Okay? So 10 minutes goes by. I remeasure the balloon here. It's at minus 38 degrees Celsius. Well, that's fine, but I can't put that into my formula here. So what did I tell you guys to do yesterday? I said if I give you Celsius, you add 273.15 to it. So negative 38 plus 273.15 gives you 235.15. That's going to go here. And the pressure is now 80.5 kilopascals. 80.5. Okay? So, you know, once again, you're done. Okay? You got V2 here, you got all the numbers, you just got to put them in on your calculator. Okay? Now listen, make sure that these match up. Look, kilopascals up here, kilopascals down there. Those two would cancel. Kelvin, Kelvin, cancel. You're left with liters. Is that a suitable unit for volume? I hope so. Yeah, it is. Liters, milliliters would be acceptable. Okay? So, you solve this. Don't forget, if you're going to do this all in one step, get your calculators out and do this. Okay? If you're going to do this all in one step, okay, don't be lazy. Come on, let's go, guys. Don't forget, you got to get the right order of operation here. Brackets, yes? Don't forget, if you don't do that, you're never going to get the right answer. Okay? Type all that out. Do it now on your calculator. Make sure you're getting the same answers as I am. Okay? And I think you should get as a final answer 16 point, it's 16 point something. It is. Point what? 25. Is it not 16? No, no, I think that's the next one. 16 what? Good enough. Liters is your answer for this one. Okay? That's what you should get. If you're not getting that, okay, that's why I want you to do this with me, guys. Okay? Then you're doing something wrong. Either the number, one of the numbers you wrote down is wrong. Maybe you're not using brackets. You don't need brackets up here. Just do this times this times this, divided by bracket, bracket, this times that. Okay? And you should get 16.25. And if you're still not getting that, maybe we'll have to spend some time later. Okay? You should get that, though, as an answer. Somebody else get that just to verify? Yes? Yeah? Okay. All right. Now, that is the answer, trust me. We do need to do, we're not done. We got to round significant digits. So we go back to the question, which I actually have to go back to here then. Look, here's 3. Okay? 3 there. Here's 3. This is constants, so we don't need to worry about significant digits there. We're not measuring those. We're not measuring those. Somebody's measured those for us already, STP. Don't worry about that. Okay? This one here, though, is a measurement that was given to us, but that's only 2. Yes? Minus 38 is only 2 significant digits. Now, I know you changed that to Kelvin. I get that. You did. You changed it to Kelvin. That's fine. However, ultimately, in the big scheme of things, that's only still 2 significant digits there. It's in the question. So, when you get down to here, you can only have 2 in your answer. So, here, your final answer would be 16 liters. Okay? Final answer. So please make note of that. Make sure you look at the question. Don't worry about STP or SATP or any of those things. You got to look at the question, what numbers are in the question. Okay? That's how you would do that one there. Good? Okay? I'm going to give you a little practice with the next one here. Any questions on that one? Anyone? By the way, I'm going to refer back to this for a second here. All you're doing with this formula here, and we're going to do this again in Unit 3, all this is a comparison formula. You're comparing initial to final. It's equivalent fractions. 6/8 equals 3/4. Same thing. However, if you're going to compare stuff, because that's all this is, that's what I call these formulas, comparison. If you're going to compare stuff, you got to compare apples to apples and oranges to oranges and Ferraris to Ferraris. You can't compare a Ferrari to a Porsche because everybody knows a Ferrari's better. Right? So you got to make sure the units are the same is the point of that story. Yes? That's all that matters here. Units have to be the same. Okay, let's take a look at this one right here. This is the second one on your sheet there that had that first same example. I'm going to give you a little time to read this one over, and I want you to decide what do I need to solve for, and go ahead and solve for that in the form. I always like to start these questions with, obviously, my formula here, okay? So that I can kind of take a look here. What do I need? In this case, do I need all the formula? Do I need all the letters? Maybe I don't. Maybe I can cross them out. Maybe the pressure staying the same. Maybe the temperature staying the same. Maybe the volume stays the same. I can get rid of something here. That's not the case with this one. This one you're going to need all of them. Okay. First of all, it says here I got a 3.45 liter piston, holds gas at 30. The piston's compressed to 850, 68.5, and 135. Calculate the original pressure. So what letter are you looking for? What variable are you looking for here? Original pressure, P1. So once again, okay, it's up to you how you want to do this. I can't. P1 V1 T2 equals T1 P2 V2. I want to get P1 by itself, so V1 V2, I divide those. And if I'm going to do that there, I'm going to do that there as well, right? This stuff cancels, and I'm left with P1, okay? That's what I do. You know, honestly, some of you guys look at that and maybe can rearrange it in your head, okay? I'm not going to brag, but that's me. I hope so. It should be, okay? If not, I'd be worried, guys. I don't care. Just don't mess it up, right? If you need to spend the time and you got your own system, that's fine. But ultimately, that's what we need to end up with. So if you did that, hopefully that's where you're at. Hopefully you're able to do that part. Okay? Next, move the question way up there, but it's a 3.45 liter piston at 30 degrees Celsius. That's the initial conditions. So let's find that here. So what are they telling me? Once again, 3.45 liter piston, that's V1. So 3.45 liter piston. Okay. At a temperature of 30 degrees Celsius, that would be T1. So this would go here, 303.15, T1, and V1 are what I know so far. The piston compresses until it's 850 milliliters, so that's V2. But look, this is what I'm talking about. the units have to match up. You can't put 850 in there because you can't compare milliliters to liters. That's like the Ferrari and the Porsche. You know, not the same. So we got to make sure those two units are the same. Okay? How do you change milliliters to liters? Well, you'd move it 3 places over to the left, milliliters to liters. Could you change them both to milliliters? Sure you can. You'll get the same answer, promise, I promise. I'm not even going to bother doing it. Trust me, you get the same answer. But you got to change both of them to milliliters. They will have to be both the same units. Until the temperature is 68.5, there's no point in worrying about that. Let's see, 68.5 and 273.15 is 341.65. That's going to go here. Kelvin, of course, yes, and 135 kilopascals. That's going to go here. I hope. Yeah, P2. Yeah. Once again, multiply those together. Okay, and make sure you use brackets accordingly. Do this for me now, guys. Make sure we're on the same page here. Actually, don't remember the exact number, but somebody can help me out maybe. 29.551. Sorry. What? Good enough. Okay, thank you. Okay. 3 significant digits. Go back. You know, all these numbers. If you go back and look at this, all have 3. Okay, they're all 3 guaranteed. So final answer, all said and done, 29.5 kVA. Okay. Make sure you can get that on your calculator. If you can't, don't worry. Okay, but come see me so we can fix it. That's the important thing. Okay. Yeah. Yeah. All right. Good. Yes. Good so far. Those are the toughest ones. Okay. That's it for now. Those are the toughest ones. Relax. All right. However, we'll look at one more. I'll mention a few things here that we need to do before the end of today here. So I want to keep going here. This one here is the top of the next page one. We'll just do this one real quick with you here. And then I promise you we'll quit and we'll talk a little bit and we'll have some time to do questions. Don't worry. They're not due for tomorrow, etc. So just relax. Okay. This one here, 2,500 milliliter piston contains air at 20 degrees Celsius. The volume decreases to 750 while maintaining a constant pressure. Then what's the new air temperature in Celsius? Okay. So the first thing when I look at this, I think, well, geez. First of all, I probably should start with my formula. Okay. With all of these. Maybe I got to use all of them. Maybe I don't. But I know that's my formula. This is on the back of your periodic table, guys. It's the only one I give you. Okay. Well, only not. I don't give you boiled water individually. I just give you this one. This does all. Okay. Notice it says maintaining a constant pressure. We don't need to worry about pressure. Take it out. Okay. Really, what do you have? You got this. That's all we probably need to worry about because the pressure is going to be the same anyway. Just take it out of that system. Take it out of that equation. V1 T1, V2 T2. When you see that, and I say, hey, what law is that? You should tell me it's, say it, somebody. Whose law is that one? Volume and temperature, you should know. That's something I expect from you. The answer is Charles. Okay? So, put in the number, or sorry, we need to solve for the new air temperature. The new air temperature, of course, will be T2, yes? So, I want to solve for T2. Little cross multiplying here. V1 T2, T1 V2, cross multiply and solve. Okay. I want to solve for T2. What's the new air temperature going to be? Divide both sides by V1, yes? Okay. Like I said, if that's confusing for you, come see me. Okay, and we'll work out a system for you that works out. Okay, I got lots of them. Not lots of them. I got like 2. But something will work. Okay, worst case scenario. So, okay, so there we go. Obviously, we have some numbers here for us. So T2 is equal to T1 V2 over V1. Let's see. T1 is what? 20 degrees Celsius. 20 degrees Celsius. 293.15 Kelvin. right? V1, 2,500 milliliter piston. That's got to be down here, 2,500 milliliters. Okay. Decreases to 750. That's my new volume. What is T2 going to work out to be? Okay. So we're going to multiply that, divide. We don't really need to worry about brackets in this case. I'm going to have to move it down here, guys, a little bit. So T2 works out to be, I believe it's 89 point. What is it? I did it again. 87.945. Now, listen. One of the things you have to keep in mind is, right, what did I just solve here? I solved temperature. Look at the units you used here. Milliliters, milliliters, those cancel. Anytime you solve for the formula here, that's in Kelvin, right? Right? Okay, because it's part of the formula. The question says, what's the new air temperature in Celsius? So I'm going to bring this up again when you're doing your worksheet here. Subtract 273.15. If I give you Kelvin, okay, we did this the other day. If I give you Kelvin, you subtract 273.15. Okay, so we're going to do that. Let's see here. 87.945 minus 273.15, and you get a negative 185.205 degrees Celsius. Okay? So don't forget about that part. This is only a 4-variable formula, but we already got more stuff involved with this one, yeah? Then you say, okay, that's fine, but I guess we still need to talk about significant digits. So we go back to the question, we say, okay, well, this one's got 4, this has got 2, and this has got 3. So I guess I probably should only have 2 in my answer then. So I go back down here and I say, how am I going to get 2? Even if I did a negative 185 degrees Celsius, that's still 3. So the only way to get 2 is scientific notation. Okay? So you can see the problem here. Well, let me just do this first. Do you agree those two numbers are the same? Scientific notation-wise? Those two numbers are the same, yes? They are. Negative 185 is negative 1.85 times 10 to the 2. Problem still got 3 significant digits. So you need to do some rounding here. Negative 1.9 times 10 to the 2 degrees Celsius. Final answer. Okay? So there's quite a bit involved with that, especially at the end. Okay? So don't forget, that's how we're going to combine all this stuff together. I know we kind of just did pressure conversions, we did some temperature conversions, but don't forget about that stuff for this here as well. Okay? All right? Okay. That's all the examples I'm going to do with you guys, but I'm going to show you one real quick here. I'm not going to do it, I'm just going to show it to you, and we're going to talk about some stuff for tomorrow, etc., here. Take a look at this one's. There's a bunch of more examples in your sheets there. There's probably another 4 if you want. If you want to see another example, come and see me. I'll do some more with you. Okay. If you want to practice practice more, do them, ask me, whatever. But there's more examples there for you to do if you want to. Okay. I'm going to give you a worksheet on all this stuff right away here, and we'll talk about what that's going to involve. One of the examples in there is this one here. Okay, and you don't have to, you can just look up here if you want. When you read this through here, hopefully you understand the first thing first is, you know, how would I approach this question? Like all the other ones, I'd say, here's my formula. Do I actually need all 6 variables there? And the answer to this one is no. Determine the volume of this gas at the same temperature. Temperature staying the same, so I would get rid of probably the temperature if I were you. Yeah? That, of course, is Boyle's law, you would say. Yes? Pressure and volume. Right? So there's Boyle's law. Fine. What's the biggest problem with this question? Can I just stick numbers in? Good to go? And ATM, right? Those two pressures are not the same units. You most certainly cannot just stick them in this formula because it's, like I said, to be old Ferrari and Porsche. You can't compare them, okay? You got to keep the same units. So now it's your decision. And it doesn't matter which one you do, but you either need to change this one into ATM so that you got ATM and ATM, or you need to change this one into millimeters of mercury so you got millimeters of mercury and millimeters of mercury. Okay? Doesn't matter. And if you want, you can change both of them to kPa or PSI for that matter. I really don't care if you want to do more work, but I would pick one and change it. Okay? That's going to be a little challenging for you guys, and I'm going to kind of let you guys work on that a little bit on your own when you get to the worksheet there. Not all of them are like that, okay? But unfortunately, when you get to that kind of question, there's a lot more work involved, okay? So I just wanted to show you that this is how we combine the temperature conversions, the pressure conversions, and all that stuff, okay? So just be aware of that. Tomorrow, you're going to have a quiz. 5 questions quiz. And 5 questions are going to be made up of the following, okay? The 5 questions are going to be 3 pressure conversions, okay? And all that it's going to be is, I'm going to say 12 psi equals how many ATM. That's what it's going to look like. You're going to have 3 questions like that, and I want you to change pressures, okay? 3 of those, and then 2 temperature conversion ones. So if I give you Celsius, how many Kelvin is that? Okay, and then I'm going to give you a Kelvin one, not a big shocker I don't think, and ask you how many Celsius, just to make sure we're able to do that. 5 questions, that's it, okay? After that, you're going to work on your worksheet that I give you today here, okay? So that's that. Okay. I think that's all I need to tell you about that.